Nicolas' talk. It's not mine. Okay, it's a joint work with Cello Martinez and Efim Zelmanov, and it's about the classification of cuspidal modules over superconformal algebras. So let me explain what a superconformal algebra is first. And this is a Lie superalgebra J equal sum of with a grading over Z, which is simple. So it's a Lie superalgebra, not algebra, which is simple, and the dimension of Gn is uniformly bounded, and the main condition is that J contains the Vir algebra, which is centerless Vir algebra, which is a derivation of C of t and t minus 1. And there is the full classification is not known. There is a list of such superalgebras. And basically, there is the Lie algebra Wn. Wn is a Lie algebra of all Lie superalgebra of all derivation of C of t, t minus 1, zeta 1, zeta n. Here, zeta 1, zeta n are odd variables. And in what follows, all superconformal algebras are vector fields in dimension 1n. So we just forgot the even dimension 1 because it's always 1. N denotes the odd dimension. There is also a subalgebra Sn gamma, those in Wn which preserve some volume. And there is a more interesting series which is called Kn, contact series. Sorry, contact superalgebra, which are of two types. There is Kn, which is called of Ramond type, and KNSN, which is Neuve-Schwarz type. But when n is even, the Ramond type and the Neuve-Schwarz type are isomorphic. And so in the even case, there is also a twist form of K2n, which is denoted like this, which is K2n, all contact things fixed by some involution. And it's a contact structure on C of t, t minus 1, zeta 1, zeta n. I will not provide a precise definition. And in addition of that, there is an exceptional superconformal algebra, which is called CK6, which is called Chern-Katz superalgebras. And so our main result is a classification. Sorry, I have to define what cuspidal modules are. So cuspidal modules are J modules M with a grading. So here, when I consider a Z grading, I mean each homogeneous component is finite dimensional, and we assume that the degree, the set of degree of M, this is a set of N, such that Mn is not 0. We assume that this is not bounded below nor upper bounded. So a Cuspidal module is a simple G module M with all these conditions. And our main result is a full classification, full and explicit classification of all Cuspidal modules over all non-superconformal algebras. And also over their universal cover, their central covers. So we do consider also Cuspidal modules with non-zero central charge. And there have been many previous work by Kai, Pei, Xia, Lu, Liu, Kashuba, Yohara, Billig, Futorni, and it was all this work provides a non-complete answer. It was special cases, and in our presentation is extremely explicit, so it's difficult to compare with previous results. And what I will do in my talk, I will concentrate not on the general picture, but on the exceptional part of the classification. Because this exceptional part is probably the part which is the most relevant for mathematical physics. And so I will try to explain first something that I call the defect in the theory. And the defect involves some contact algebra. So Kn, the contact algebra, is a contact structure on C of t, t minus 1, zeta 1, zeta n. Basically, it means that it is a Lie algebra structure on this ring, such that the adjoint action is given by a differential operator of degree 1. I will not describe the explicit statement. And for n different from 4, Kn is simple. So it is a superconformal algebra. But for n equal 4, it is not the case. So for n equal 4, we define now K4 as the derived algebra of K4. So this is a definition not for mathematicians, but for computers. It means the new definition of K4 is a derive of the old algebra K4. Of course, this is mathematically it's a bit dubious, but it means this is my new notation. And what is missing in K4 is a monomial zeta 1, zeta 4, zeta 1, zeta 2, zeta 3, zeta 4. This monomial is not in the derived algebra for n equal 4. And now I came to central extension, to projective representation. Cuspidal modules. So all central extension for all non-superconformal algebras have been computed by Katz and Vandeler. And there is exactly, I think, something like 10 J, 10 superconformal with 10 or 11 H2 of J is not equal to 0. And in all cases, the H2 has dimension 1, except that H2 of K4 has dimension 3, and I select one specific central extension of K4 that I denote by K4 hat. It means that among this space of dimension 3, or exactly among this space of dimension 2, because central extension only depends on the projective space of that, I select one specific element, and I denote by the corresponding central extension K4 hat. And now the first result is the following. The theorem 1, that the superconformal algebra J, or any cuspidal, and projective J module by projective I means representation of some central extension as zero central charge except one specific case, except if J equal K4. Only one exception. And for this case, it is exactly a K4 hat module. It means that if you have a non-zero central charge, it comes from exactly one central extension of K4 and nothing more. And that's a bit, it's a bit a surprise, because for the Lie algebra Vir, if you take a cuspidal Vir module, it has zero central charge. This has been proved. This has been proved by myself in 1992, in an old paper of mine in 1992. So that's really a bit surprising that there are some central charge for modules which are cuspidal. And I will not now describe very precisely our result, but basically we have embedding like this. First, K3, or the Neuve-Schwarz form, as well that K for the twist form, all these Lie superalgebra lives inside K4 hat. A priori, these three superalgebras are living in K4, not in K4 hat. It means that the central extension, this central extension, restricts trivially on these three superconformal algebras. And also, K4 hat lives inside, say, K6. And the main result is something like this, is that one, most of the time, simple cuspidal module are indexed by triple lambda delta u, where lambda is a dominant weight with lambda of h1 equal to. What's the meaning of this? It means that inside all superconformal algebras, there is a kind of maximal simple or semi-simple Lie subalgebra of finite dimension. And for this Lie algebra, because our theory is about highest weight description, there is a notion of simple roots, and we index the simple root in a way that H1 plays a specific role. I have to say that when, for example, for K2n, the corresponding Deakin diagram of the simple Lie algebra living inside K2n, it's SO2n, and they index the ways like this: 1, 2, 3, blah, 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 n. So you see my index is not like in Bourbaki. 1 and 2 are the simple root or simple coroot at the fork of the Deakin diagram. And for K2n plus 1, the 1 is exactly the long coroot or the short root. But this is a general case. But the K4 hat modules, representations, theory, impacts representations of K3 of all superconformal algebra which are very close to K4 hat. That means and CK6. Its impact representation theory of all these superalgebra which are directly connected with K4. This is subalgebras And this one, CK6, as we have seen before, it is a superalgebras. The first sup means it contains K for hat, and the superalgebra because it is a superalgebra. And in that case, representation theory is described as follows. In that case, Cuspidal are indexed also by dominant weight lambda with lambda of H1 equal 1, but then there is a condition with condition about delta. For example, for K3, it is possible to have lambda of H1 equal 1, but then delta has to be 1/4. For K for hat, it's very complicated. It's lambda of H1 equal 1, then delta equal lambda 1 over 2, and then the central charge, lambda c, has to be lambda 2 over 2 lambda 2, sorry, or lambda of H1 equal 1. There is two possibilities, and delta equal lambda 2 plus 1 over 2, and lambda c equal minus 2 lambda 2. And for CK6, there are conditions like lambda of H, if lambda of H1 equal 1, then delta equal lambda 1 over 2, and lambda of H3 is 0. So for CK6, let me explain. CK6, in van der Rohe-Katz's description, it contains SL4, but we can see SL6, sorry, but we can see SL4, sorry, which is the same as SO6. So in that case, the way to index the Dynkin diagram is like this: 1, 2, and 3. Okay, we consider the maximal simple subalgebra as a type D, not of type A. So in that case, the index is 1, 2, 3, like this. So of course, the way I describe is extremely imprecise, but our preprint, which is now on archive, and in 2025, is very long. It contains 170 pages. And next, I have to describe what's going on for the case of twisted contact algebras. And for twisted contact algebras, there is a kind of description which is a bit complicated. It shows that any K2 to N module, Cuspidal module, is either simply a Cuspidal K2N module, or it is of the form V, the fixed point under sigma of V, where V is a cuspidal K2n module. Sorry, K2n module. And these two cases are explicitly described in terms of the highest weight of V. So basically it means that and here in my explanation, I mostly explain the case, the contact case. And here again, there is an exception. Exception is for K to 4, the twist 4. It is the same that except it is either K4 at cuspidal module or the fixed point of a K4 at cuspidal module. And you see what is very strange in this theory is that K3, if you take this algebra, K3, the Neuer-Schwarz form of that, when you take the twisted form of K4 and CK6, okay, any cuspidal module has 0 central charge. But still, the representation theory of all these super algebras are completely influenced by representation not of K4, but the central extension of K4. And in some sense, the central extension of K4 plays a kind of hidden role inside the representation theory of all of these superconformal algebras. So I would like to thank you very much for your patience. The full work is very long, so I cannot give more details. And before I finish, I would like to express my big admiration for Ukraine, which is now fighting for democracy and freedom. Thank you very much. Thank you very much.
Thank you, dear Olivier, inspiring talk. Thank you very much. Dear colleagues, we have 1 minute for question or remark. Any questions, remark, comments? Let us try to be more active. Any comments? Questions? No? Thank you, Professor.
Okay, thank you very much.